It is the 8th of September, 2025, approximately 7:43 a.m. Continuing on with the exercises that we were working on earlier, with the mention of on problem 30, I was wondering about like the infinite case. Well, the LCM in that case is it's extended onto the naturals unified, well, in union with the set containing infinity. So that's something. It's just a sort of conventional thing. It's interesting. Where were we exactly? So yeah, so we got past 30. We discussed the finite case, and we weren't too sure about the infinite case, and then I looked into it, and the infinite case follows from that extended definition of the least common multiple. Now, 31, we were asked to prove that any finite group G of even order contains an element of order 2. We did that using the function T of G. Remember? Okay. So 32 asks us if X is an element of finite order in a group G, prove that elements 1, X squared, all the way up to X to the n minus 1 are all distinct. So that I don't believe we have done. So we'll work on that and we'll continue on with the rest of the problems. Let me check the camera first. Camera's good. Sound is a bit of an issue because of the phone case that I've got on there, but we'll see about improving that as time goes on. So exercise 32 says that if X is an element of finite order n, more specifically in a group G, prove that the elements x squared, all the way up to x to the n minus 1 are all distinct. Deduce that the order of X is less than or equal to the order of G. So what's the intuition for this, right? Well, order n means X to the n is equal to 1, and no smaller positive power is equal to 1. If two powers, if two powers, x to the s and x to the t, with s being less than t, were equal, canceling x to the s would give x to the t minus s is equal to 1, with 1 less than or equal to t minus s less than n, contradicting the minimality of n. So again, we have that minimality argument. You know, expect that to come up any single time that we deal with the orders of elements. So, well, the order of anything really, it'll probably come up. Not always, but you know, a lot of the time with what we're seeing. You know, so let's go ahead and try to prove that more rigorously. So, for the proof, let's go ahead and assume that the order of x is, well, equal to n, and that is less than infinity because it is finite. So we can say that x to the n equals 1. And x to the m is not equal 1 for every integer m with 1 less than or equal to t minus s less than n, contradicting the minimality whoops. Just started transposing the, well, transcribing the intuition there. That's not what we need, right? For every integer m, such that, well, with every integer m with 1 less than m less than n. And so you can sort of see how that was going there with the intuition, but you know, we're proceeding here with steps here in a rational process. So assume the order of x is equal to n, which is less than infinity, so it's finite. So x to the n is equal to 1, and x to the m is equal to 1 for every integer m with 1 less than or equal to m, which is less than n. Right, because that's how the order of an element is defined. Now let's check for distinctness to reinforce what we know or find something that we don't. So distinctness of 1 x all the way up to x to the n minus 1. That's something we want to look at, right? So let's kind of suppose that they're not. Suppose for contradiction that x to the s is equal to x to the t for some integers with 0 less than or equal to s less than t less than or equal to n minus 1. Suppose that that's the case. That for each of these individual things, we have that they're not distinct. In fact, this is a fancy way of saying they're not distinct. Right. So what we get if we right multiply both sides by x to the negative s is that x to the s times x to the negative s is equal to x to the t times x to the negative s. Well, let's compute this a bit more in detail, see what we find. Well, x to the s times x to the minus s, that's just equal to the identity element. So 1 is equal to x to the t times x to the minus s, which is equal to x to the t plus negative s, which is equal to x to the t minus s. Now, since we've established t minus s is greater than or equal to 1, let me see. Did we establish that? Let me think about that. No, we did. Because that's part of the opening statement there, right? So Actually, let's see. Yeah, if we take our initial thing, right, we subtract, if we were to subtract s from each and every single one of these and then multiply by -1, well, after subtracting n, that's what we get here as well. Matches up with the intuition we had earlier. So, but yeah, since t minus s is greater than or equal to 1, we can say, and fitting in with the manipulation of the inequalities there, we get that t minus s is less than or equal to n minus 1 as well. This says that x to the m is equal to 1 for some m integer, with 1 being less than or equal to m, which is less than n. Which means we get a contradiction, because we had earlier the definition of n as the order of x. Definition of n as the order of x, so just what we assumed there from the get-go. Minus 1 plus 1 plus 1 and minus 1. Let's see how that works. All right, plus 1. Something like that, where subtract n, you get -1. I'm just going back to the inequality here to just to show a bit more explicitly what I mean whenever I say the manipulation of the inequalities. This is what I'm getting at. So, if you were to subtract s from this, which is greater than or equal to 0, well, it's only ever going to be less than or equal to n minus 1. Subtract n from both sides here, right? So, and then you get that t minus s is less than or, in fact, equal to -1. Then, well, you take just this part, right? And then you multiply. You say, okay, let's switch the signs around. And if you switch the signs around, what you're going to get, of course, is that t minus s is greater than or equal to 1. So what we wanted, so if you're wondering about why this shows up, wonder no longer if that suffices. If it doesn't, well, then look at it more closely and evaluate that with your heart of hearts, in a sense. But let's continue onward. The definition of n as the order of x, it contradicts that directly, because it can't be that way, because of the way that the definition of the order is established, right? So let's continue along this line of reasoning, sort of determine if these are in fact distinct. Well, what we find is that, our assumption led to a contradiction. Therefore, that assumption has to go. Therefore, no such s no such x to the s equal x to the t exists. Can't say that that's the case. That was our supposition. Now, what can we then say? Well, we can't say that from that follows that we have instead pairwise distinct, because these things can never equal each other, and these were chosen arbitrarily. So 1 to the 1x, x squared, all the way down to x minus 1, those are distinct, pairwise distinct. That's what we wanted for distinctness, but then we have to do the deduction part of it all, right? So let's go ahead and move on to that. Now, let's move on to the deduction. So, we're supposed to deduce that the order of x is less than or equal to the order of g, right? So, how do we go about saying that? Well, let's just go ahead and label this 2 since this is the second part, right? So, the cyclic subgroup generated by x is cyclic subgroup generated by generated by x is subgroup x such that, which is the set such that x to the k such that, which contains x to the k such that k is within the integers, is an integer, right? So because x to the n is equal to 1 and the n elements 1, x, all the way up to x to the n minus 1 are distinct, like we showed, we have that the order of this subgroup generated by x is in fact equal to n, which is equal to the order of the element x itself. So since this is a subgroup, a subset of G, it follows by definition of the subset, order and all that's good in the world, right? So that the order of x is equal to the order of the subgroup, which is a subset of G, which is less than or equal to the order of G. That's how subsets work for the outer set, the set itself. So we can sort of inherit that. We inherit that process. We inherit that property from the subset set relationship, subset set order relationship. So too, we sort of inherit that from so too do we have that here with subgroups and groups. But this is a way of saying it more line by line in order to get to that point. So that's an interesting thing. And that pretty much is it for going 1 all the way up to 32. Move on to 33 now. Try to do a quick camera check. So we're just about out of problems for 1.1, which is good. So that way we can get on to the other problems in the book. Yeah, that looks good. So let's get on with it and go to exercise 33. Now, exercise 33, well, we have let x be an element of finite order, n in the group G. So for 1, we are asked to prove that if n is odd, then x to the I is not equal to x to the negative I for all I equal to 1 to such and such so and so, all the way up to n minus 1. Follow that pattern all the way up to n minus 1. Now, for B, for part 2, we're asked to prove that if n is equal to 2k and 1 is less than or equal to I, which is less than n, then x to the I is equal to x to the negative I if and only if I is equal to k. So let's see, intuitively speaking, x to the I equals its inverse means that x to the I is equal to x to the negative I, right? So, which forces x to the I times x to the I to be equal to x to the I times x to the negative I, which is equal to 1, the identity element, what have you, and that implies that x to the 2I is equal to 1. So the order n must divide 2I. If n is odd, this makes n divide I, which is impossible for 1 being less than or equal to I, which is less than or equal to n minus 1. If n is even, say n is equal to 2k, then 2k divides 2I means that k divides I, leaving only the midpoint I is equal to k among 1 less than or equal to I less than 2k. So let's look at this more rigorously. So let's just go through each of these in turn, right? So, well, first of all, assume throughout that the order of x is equal to n, which is less than infinity, so it's finite. So x to the n is equal to 1. We're going to assume that x to the n is equal to 1, and n is minimal with this property, right? It's not really an assumption so much as like, well, it is an assumption, but it's like we know that to be the case, and we can't really do any work if that's not the case. So what's really the point if we weren't to assume that this was the case, right? We're just stating what's obvious on the surface right there, just so that we can have it, see it, work with it a little bit more tangibly in a sense. So let's go with let's go with part A first. So if n is odd, then x to the I is not equal to x to the negative I for 1 less than or equal to I, which is less than or equal to n minus 1, which is essentially what we were saying whenever we did that little I is equal to 1, 2, on and on until we reach n minus 1. So let's suppose toward a contradiction that x to the I is equal to x to the negative I for some I with 1 being less than or equal to I, which is less than or equal to n minus 1. So let's multiply both sides by x to the I. What does that get you? Well, that gets you x to the I times x to the I is equal to x to the minus I, x to the negative I, times x to the I. And like the previous example, we do so here, where we compute both sides explicitly, and what we end up getting is that, well, let's make note of that. Compute both sides explicitly. We get x to the 2I is equal to x to the negative I plus I, which is equal to x to the 0, which is equal to 1. So, thus, x to the 2I is equal to 1. So, the order n divides 2I. Divides 2I. Now, n is odd. And since n is odd, the GCD between n and 2, well, that's equal to 1. So from n divides 2I, it follows that n divides I, but 1 is less than or equal to I, which is less than or equal to negative 1. So let's just, so in a moment, I'm just going to translate this over to make this more apparent whenever I say it. But, so we say here that, so from n divides to I, it follows that n divides I. But we have that 1 is less than or equal to I, which is less than or equal to n minus 1, which is a contradiction. The reason it's a contradiction is that n can't divide I. Why might that be? Well, rearrange these inequalities. We get 2 is less than or equal to I plus 1, which is less than n. Fair enough, right? So that would be less than or equal to that, no matter, less than or equal to n no matter what. Well, not no matter what, but say we subtract n from this side. Is it going to change the fact that it's less than n? It's like, no, it's not going to change the fact that it's less than n. What we end up getting is that, 1 is less than or equal to I, which is less than equal to n. So, which should be, well, does it make it absolutely, I mean, suffice to say that it's less than, it's actually less than n in that case, because we're subtracting 1 from it whenever here we had that it was less than or equal to. But what we have then is that, okay, can n divide something which is less than itself? It's like, well, no. So we have as a contradiction that n cannot divide I. Correct me if I'm wrong, but that's sort of the crux of it. Now, and because of that, we say that as n cannot divide I, and because of the fact that n cannot divide I, well, we say that, well, n is odd. Well, no, sorry. Let me take a step back here. N cannot divide I, therefore, no such I exists. That is to say, x to the I does not equal x to the negative I. So, well, does not exist for all I from 1 to n minus 1. Because we assumed that this was the case. We found a contradiction along the line of reasoning that resulted from that assumption. So therefore, we say that the assumption is incorrect, leading us to adopt its converse, its opposite, its other, which is that x to the I is not equal to x to the negative I. Quick camera check, and then we'll move on to the next part. Well, at least for the purposes of this context, n cannot divide anything less than itself. There's probably some weird thing out there, It's like, well, we find out that the LCM had an extended definition to include infinity. It's probably like, well, there's probably something out there where it's like, yeah, you can actually do that. It's just that it needs to be in this interesting context, but we're not discussing that interesting context right now. We're operating within this context, so it's not going to be the case, and this works. Hunky dory. I don't know though. I feel like there's no context where that would actually be useful. But I've been proven wrong before. So, part B. Part B states that if n is equal to 2k, we want to prove that if n is equal to 2k and 1 is less than or equal to I, which is less than n, then we have to have that x to the I is equal to x to the negative I, and that this occurs if and only if I is equal to k. So we're given that n is equal to 2k and 1 is less than or equal to I, which is less than n. So we just have to prove this bijective statement. So let's go the if then, the normal way, well, the right to left way. Assume x to the I is equal to x to the negative I, with 1 being less than or equal to I less than n. So that's our assumption, and with the above case being intact as above, so below, no. As above, x to the 2i is equal to 1, and that implies n divides 2i. That implies 2k divides 2i. That implies k divides I. Now, since 1 is less than or equal to I, which is less than 2k, and k divides I, the only possibility is I is equal to k. So we have the left to right. I said right to left, I was mistaken. Left to right. That's how we read in the English-speaking world, right? So we have the left to right way established. Now let's do the right to left case. Can we get there? So conversely, may have misused conversely there earlier. Oh well. What I said was proven anyway. So x to the I is equal to x to the k. X to the negative I is equal to x to the negative k. So conversely, if I is equal to k, then x to the I is equal to x to the negative k. And x to the k times x to the k is equal to x to the 2k, which is equal to x to the n, which is equal to 1. Just check that just to make sure it makes sense. That makes sense. So x to the k is its own inverse, which that is x to the k is equal to x to the negative k. So we have that it's proved either way, and going back to this, what does this mean? Well, this means that x to the I is equal to x to the negative I. So we have it proved both ways. So that is it for 33. Now we'll move on to 34. So for 34, we have if x is an element of infinite order, in G, prove that the element x to the n, in which n is an integer, are all distinct. So similar to the last one, but this one's more specific to this case. Of course it is, because that's, what else would you have in that case? Okay, so let's see. Intuitively, how do we approach this? Well, infinite order means no positive power of x equals 1. If two powers coincide, say x to the m is equal to x to the n with m not equal to n, cancel to get x to the m minus n is equal to 1 with m minus n not equal to 0. That would contradict the definition, and we have it. So let's see what this means a bit more rigorously. Assume, see, what does this mean for the previous one? See, okay. So assume the order of x is equal to infinity. We show that if x to the m is equal to x to the n for m n integers, comma, then m is equal to n. So let's suppose that x to the m is equal to x to the n. Now, without loss of generality, we can take n to be less than or equal to m. Now, let's multiply by x to the negative n. And get there is that x to the m is equal to x to the n, right, as earlier, and so we multiply, and then what we get is x to the m, x to the m times x to the negative n is equal to x to the n times x to the negative n, and then, well, compute both sides, and what we have here is that x to the m minus n is equal to x to the n minus n, which is equal to x to the 0, which is equal to 1. Now, if m is greater than n, it's supposed to be an m. Well, is it? Is it supposed to be an m? No, it's not. No, it's not. Because we said we're equal to, so. Okay, so if m is greater than n, m minus n is contained within the positive integers, and x to the n m minus n is equal to 1, which contradicts the absolute value, the order of x to be infinity. Hence, m cannot be greater than n, so m must equal n. Therefore, no two distinct integers yield the same power. That is, the elements contained within the set x to the n such that n is an integer are all distinct. Just what we wanted. Let's think about this. Suppose it could be different because it's not. It couldn't be different. It has to be equal. Because it's equal and because we chose them arbitrarily, they're the same thing. Right? So, essentially. Now we'll move on to 35. Pins keep on breaking. Probably shouldn't have put so many on here, but it's fine. 35. Let's go on to 35. So for 35, we have if x is an element of finite order n in G, use the division algorithm. Oh boy. Use the division algorithm to show that any integral power of x equals one of the elements in the set containing 1x, x squared, all the way up to x to the n minus 1. So these all the distinct elements of the cyclic subgroup of G generated by X. Okay. So intuitively, well, it's like, well, the order n, that means x to the n is equal to 1, like always. For any integer exponent k, divide k by n, we get k is equal to qn plus r, with 0 being less than or equal to r, which is less than n. Then x to the k is equal to x to the qn plus r, which is equal to, open parentheses, x to the n, close parentheses, to the q, times x to the r, which is equal to 1 to the q, times x to the r, which is equal to x to the r. So every power collapses into the first n powers, 1, x, so on until we get to x to the n minus 1. So how would we say that more rigorously? Well, read proof, which I'll get to here after I erase this. So we'd assume we have a finite, we get these things at a finite order. Assume x is equal to, gosh dang it, is equal to n, and assume that n is less than infinity. So x to the n is equal to 1 by definition of order. For any integer exponent k, divide k by n. And what we get is k is equal to, transcribing the intuition again. But for any, yeah. Or that. Good. Okay. So, well, instead of that, let's let k be an integer and let it be arbitrary. This is where the rigor all comes. So by the division algorithm, there exists unique integers Q and R with K is equal to Qn plus R and 0 is less than R, which is less than N. So let's compute x to the k here. X to the k is equal to x to the qn plus r, which is equal to x to the qn times x to the r, which is equal to, open parentheses, x to the n, close parentheses, to the q times x to the r, which is equal to 1 to the q times x to the r, which is equal to x to the r. And with, of course, this being true, 0 being less than r, which is less than n. So we can say, hence, x to the k equals 1 of either 1x squared until we get to x to the n minus 1, right? So now for showing that these are pairwise distinct, we already showed that earlier, right, with exercise 32. So let's make note of that. By exercise 32, we have that 1x all the way up to x to the n minus 1, that those are pairwise distinct. When the order of x is equal to n, these are precisely the n distinct elements of the cyclic subgroup generated by x, which is equal to the set containing x to the m, such that m is within the integers. And we were asked, okay, x is an element of finite order in G. Use the division algorithm to show that any integral power of x equals one of the elements in the set. So these are all distinct elements of the cyclic subgroup generated by x. We used the division algorithm. We showed that this was the case. We showed that these are all distinct. So this is a complete proof. Yeah. Now we can move on to 36, which I believe is the last of the 1.1 problems before moving on to the 1.2 problems. Whoa, 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 whoa. Okay. So, example 35, gas if X is an element of, well, actually, that's not it. Let's see if it actually is it whenever we looked at actual 36. No, no, it is not it. I was just rewriting 35. Okay, well, shouldn't be doing 35, we're on 36. 36, assume G is equal to the set containing 1, A, B, C is a group of order 4. With identity 1. Assume also that G has no elements of order 4. Use cancellation laws to show that there is a unique group table for G. Deduce that G is abelian. Okay. Well, that's supposed to be lowercase because it's just supposed to kind of fade into the background nowadays. Whew, okay. So let's talk about this a bit more intuitively. With the order of G equal to 4 and no element of order 4, every non-identity has order less than or equal to 3. An even order group has an element of order 2, and once one involution is present, cancellation forces all remaining products. A short check would show every non-identity must square to 1, yielding the Klein 4 group. But let's try and look at that a bit more rigorously to see exactly what I mean by that. Okay. So for the proof, let G be equal to the set containing 1, A, B, C, that's it. And assume no element has order 4. No element has order 4. So for step one here, pick an involution. So since the order of G is even, there exists X within G with X squared equal to 1. such that a squared is equal to 1, which is more appropriate to what's actually in G, right? So that's why. Step 2, determine AB, BA, AC, CA by cancellation. So for AB, there are 4 possibilities in the set containing 1, A, B, C. Either we have that AB is not equal 1, plus else B is equal to A negative 1, which is equal to A. So 4 possibilities in that, because we're multiplying each of those together. B squared cannot equal 1, unless B is already equal to A, in which case it's not distinct, in which case it shouldn't even be a thing that's mentioned, right? So, let's see, can A be equal A? Well, if we left cancel, then we'll get that B equals 1. We can't have that. So no, AB cannot equal A. Now, let's see about this. Can AB equal B? Well, no, and for the same reason that if we right cancel, right? If we right cancel, gets A equal to 1. That's not a distinct thing, so, because these are supposed to be all distinct things, they can't equal each other. So what we do have, though, is that AB equals C. That holds. And this same argument, actually, this involving the interchanging roles of left-right cancellation and a BC, same argument. The same argument of interchanging roles of left-right cancellation. Well, that gives you BA is equal to C, AC is equal to B, CA is equal to B. Now let's see about that. See about how this holds up whenever we go on to the next step. Let's hope on this. That's better. Go ahead and go about that, shall we? So, step 3, want to relate b squared and c squared, then rule out order 3. So, using b is equal to ac, AC, and b is equal to CA, we compute b squared is equal to, open parentheses, CA, close parentheses, open parentheses, AC, close parentheses, is equal to C, open parentheses, A squared, close parentheses, C is equal to C times 1 times C, which is equal to C squared. So, B squared is equal to C squared. But if b squared is not equal to 1, then the order of b is equal to 3. Orders, this can't be, it has to be less than 4. It has to be less than 4, right? So, let me think. Has no elements of order 4, so. But the highest, the group itself is of order 4, so that's something. If the involute is not equal to 1, then the order of b is equal to 3. 1, 2, 3. What allows us to say that? Well, let's see. Okay. What is that? So like it can't be 1, can't be 2. So we try it to be, right? So the order of, if it's not the case that it could be 2, right? Then let's try 3. Then the order of b is equal to 3. Orders are less than or equal to 3, and b can't equal 1, right? So, yeah. Hence b 3 is equal to 1. Then a is equal to a times b to the power 3, which is equal to, open parentheses, ab close parentheses, b squared, which is equal to cb squared, which is equal to c squared, which is equal to c cubed. Now, since A is not equal to 1, we have C3, C to the 3 is not equal to 1. So the order of C cannot be equal to 3. Thus, the order of C is equal to 2, and C squared is equal to 1. And by B squared is equal to C squared, we get B squared is equal to 1. So B squared has to be equal to 1. Okay, so each of those is order 2. Now let's finish the table and read off commutativity. So let's see, let's finish the table and read off commutativity. So we already have and this is essential, the square is essential. A squared is equal to B squared, which is equal to C squared, which is equal to 1 squared, no, is equal to 1. So, and from step 2, AB is equal to BA, which is equal to C. AC is equal to CA, which is equal to B. So for the remaining products, use cancellation again. Which is to say, that is, BC cannot equal 1, BC, so BC is equal to A. Similarly, CB is equal to A, right? So what would the table really look like? You know, taking into account the involutes. Well, sort of think through this. Right? So let's say we have 1A, B, C, 1A, B, C. Well, for each 1 squared we get 1, A squared we get 1, B squared we get 1, C squared we get 1. What do we get if we multiply 1 by any of these, right? So that's going to be the easier part. Now it's like AC, well, that equals B, right? So BC, that equals A, CC, that, right? So how about this? AB, what does that equal? C, AC, B, B, A, C, B, C, A, and there we go. There's our table. Now, this table, it's a nice table. I'll give you a good price on it now. But this table is symmetric about the diagonal. So xy is equal to yx for all x, y within G, hence, so G is abelian. And also, which is, you know, the main part of what we're doing, there is a unique group table. Unique group table under the hypothesis. What was our hypothesis, right? Let's go back and think about that. We're given these four elements. Assume G is equal to the set containing only one A, B, C is a group of order 4 with identity 1, and then it has no elements of order 4, right? So thus there is a unique group under that hypothesis. Well, really it's two hypotheses combined into one, right? But under the hypothesis, and G is equal to Klein 4 group, right? So, which is a thing. That's a thing. Which I imagine we'll get more into. But for now, suffice to say, that's it for 36, and that's it for all of the problems within section 1.1. And we'll call this it for now.